In this video, we'll take a look at acid strength and ranking different molecules by their acid strength. So, first of all, there are 5 key factors that indicate the acid strength of a particular proton in a molecule. So first, we'll go through each one of those and explain the differences and kind of rank them in terms of which is most relevant in different situations. So first, we have electronegativity. So what we mean specifically here in the case of acid strength is that a proton, so remember a proton is a hydrogen that lacks no electrons. So a proton is simply H plus. This is a proton, just as a reminder. So a proton, like this, that is bound directly to an electronegative atom is acidic, and its acidity increases with the electronegativity of the atom that it's bound to. So let's take a look at this series to illustrate this idea. So here we're looking at these protons bound to this carbon atom. Carbon is not very electronegative, so these are a pretty weak acid. These protons are pretty weak. Then we increase our electronegativity with nitrogen. Nitrogen is bound to these hydrogens as well, so that these are more strong of an acid compared to the ones bound to the carbon because the nitrogen is more electronegative. Follow that same trend, oxygen is more electronegative than the nitrogen, so these protons are more acidic as well. And then we go all the way up to fluorine, where that proton is the most acidic out of this trend. So that is just simply looking at your periodic table and ranking the electronegativity, again, of the atom that is directly bound to the hydrogen. Like in these case, we're comparing simply the carbon to the nitrogen to the oxygen to the fluorine. Okay, now the second factor is atom size. And what we're talking about here is larger atoms bound directly to a proton increases the acidity of that proton, and it's due to poor orbital overlap, just because if you have a really large atom, hydrogen we know is really small, so that huge size difference will make that bond weaker, which is essentially why it becomes more acidic, because if you have a weak bond, then it's much more likely for it to break, which is exactly what happens when a molecule functions as an acid. You're breaking some X hydrogen bond, whatever X is. It could be oxygen, nitrogen, or halogen, something of that sort. So this best explains the following trend, which is that a HF proton is less acidic than a proton bound to a chlorine, which is less acidic than a proton bound to a bromine, and so on to the iodine. Now, this is very paradoxical, at least it was for me initially when I was learning this, because if we go to our previous trend that we just first introduced was electronegativity, right? Electronegativity would suggest that this trend would be the other way, because iodide is less electronegative than bromine, which is less electronegative than chlorine and fluorine. So that would suggest that HF should be the strongest acid out of this list. And that's incorrect. And so here it's only because the atomic size wins, basically. You have two competing factors that compete in opposite directions. One, the atomic size makes Hi the strongest acid, and electronegativity would suggest that HF would be the strongest acid. So here what we're saying is the poor orbital overlap weakens the bond more so than the electronegativity that we're talking about in the previous factor. So with that, keep that in mind, because you will see questions like this that could be confusing because you have electronegativity differences and also size differences. So most of the time, if you have a proton bound directly to an atom, it's the size of that atom that will dictate what is going to be the stronger acid. All right, the next factor is the resonance stabilization of the conjugate base. So what we mean here in the context of acidity is when the conjugate base is resonance stabilized, the acidity of the original acid that produced that conjugate base increases. And by the way, when the acid strength increases, that means the pKa decreases. So just keep that in mind, because you may see pKa lists instead of just simply an acid strength list. So a trend that is explained by this factor is that the ethanol proton is less acidic than the acetic acid proton. And let's explain this a little bit, because this is, again, another very confusing factor for acid strength. It's because you have to consider the conjugate base. So you need to recall that the conjugate base is simply the acid after it's donated its proton. So in the case of ethanol, it's just going to be this ethoxide where you have an O negative and then the proton is gone. In this case, it's going to be the carboxylate that has the O negative with that proton gone. So let's consider those options. So if the ethanol OH bond were to break and dump its electrons onto the oxygen, we would get this ethoxide now, this alkoxide that has a negative charge on the oxygen, and there's two carbons, so that's why it's ethoxide, and then that produces the free proton H+. Now, there's no resonance possibility for this ethoxide because there's nowhere that you can move those electrons, right? You could imagine forming a carbon-carbon double bond, but then you would leave these two hydrogens here on this carbon. So like, for instance, if you were to move these electrons here to form a carbon-carbon double bond, you would just have 5 carbons at that oxygen, at the carbon there, and you can't just get rid of that proton. So that doesn't happen, so there's no resonance possible for this molecule. So, but this is not the case for acetic acid. If we do the same thing with acetic acid and we lose the proton of the OH bond, then we'll put the negative charge here on this oxygen. But now again, we have this possibility to move these electrons down to form a carbon-carbon double bond, and then we can delocalize the electrons up to the oxygen and get this resonance structure. And these are equivalent molecules, but it stabilizes that negative charge because it doesn't have to be localized on the oxygen. Like if we go back and consider the ethoxide, this negative charge is stuck on the oxygen, making that more unstable. So like, as we recall from previous examples, when you have a charged species, that is less stable than if it was if it was neutral. So if we think here, effectively what you can compare this to is that you are making this oxygen less negative because it's sharing the negative charge with another oxygen, and that stabilizes it. So now the statement that we're making is, due to stabilization like this, we increase the acidity of the original acid. And this makes sense because essentially it stabilizes the product, which means that this, the initial starting material, is more reactive. A more reactive species, when we're talking about acids and bases, would be the stronger acid. The stronger acid wants to react and make the more stable product, which is this resonance stabilized conjugate base. So that is the explanation for this. So you always have to be considering, if I'm going to have an acid, if it's going to function as an acid, it's going to make a conjugate base, and I need to assess the stability of that conjugate base, because that will tell you a lot of information about the acidic nature of your starting material. All right, the next factor is the inductive effect. So again, in this context, what we mean is when you have electronegative atoms that are near the acidic proton, so not bound directly to the acidic proton, that will increase the proton's acidity. So a series that explains this is a fluorinated ethanol compared to a not fluorinated ethanol. So here we know from the previous questions that this OH is acidic because we have electronegativity at the oxygen that causes the dipole, which causes this proton to be acidic. But you can increase that acidity if you substitute the hydrogens at that carbon with the fluorine, and that fluorine will influence this proton such that it is more acidic. And the more of this electronegativity that you can add near the proton will further increase the acid strength, which is why this difluorinated species is even more acidic than just the monofluorinated. And by the way, I chose to substitute the carbon that is bound directly to the OH, but you could have a similar trend if you have it substituted at the second carbon, or even the third carbon is still going to have some influence. But essentially, the further away from the OH, or from the hydrogen that's acidic that you're trying to assess its stability or acidity of, the weaker that influence will be. So basically, the closer it is, the stronger the inductive effect will be on that proton. And the last factor to talk about is hybridization. So in this context, how it's related to acidity is that if you increase the s character of the hybrid orbitals of the atom bearing the proton, that increases that proton's acidity. So that is quite the mouthful, but just let's use this series to explain what I mean. So here we have just an alkane. These are all sp3 hybridized hydrogens, carbon hydrogens. So what that means is that we have 25% s character, 75% p character in all those hybrid orbitals. So these are not very acidic because their s character is as small as it can be. Now, if you increase this to an alkene, now the alkene carbon-carbon double bond is sp2 hybridized, which affects the proton that are involved in, or that are bound to the carbon of the alkene rather, which now they have this 50% s character nearby that proton, which increases the acidic nature of that proton. And then if you take this one step further and you look at an alkyne, alkyne has sp hybridized, which has 50% s character. So again, this alkyne proton now, the one on the carbon involved in the carbon-carbon triple bond, the terminal proton of the alkyne is very acidic because it has this 50% s character. Now, generally in organic chemistry, the hybridization doesn't influence other types of molecules besides just simple carbon-carbon bonds, so hydrocarbons specifically. The other four factors are critical for determining what heteroatom containing organic molecules, which is the most acidic. So just keep this in mind, but this is why I put hybridization last, because basically what you need to know from this is that the alkyne proton is acidic, and that will have a great influence on many types of reactions that you will proceed as you progress through the course. All right, for the remainder of the video, we will work through several example problems explaining how to use these 5 factors to rank which proton is the most acidic in the following pairs. So that is our first question here, is determine the most acidic molecule in the following pairs. In other words, which molecule has the lower pKa. Remembering that the lower the pKa, the stronger the acid. So here we have a carboxylic acid, which we know, first of all, we can go through our factors. So electronegativity of the atom bound directly to the proton. So that is this oxygen. That oxygen is the same. So in terms of electronegativity, they are the same. Both of these have an oxygen bound directly to the hydrogen. That is the most acidic one. Secondly, then we have conjugate base, which I will indicate as CB, is resonance stabilized. Right? And I'll just show as one example of this. Oops. I'll just show as one example of this, just a O negative where we lose that proton. This can resonance stabilize like we've seen before into this resonance structure. Again, remember resonance structures should be bracketed and you use this double arrow, not the equilibrium arrow. So again, I'm not showing the chlorine or fluorine, but this is the resonance structure for both of them if you add the chlorine or fluorine respectively, and they're equally stabilized by resonance. So there's no difference there. And then a third thing to consider would be hybridization. There's no difference there, right? So that can't be the reason. And then fourth is atomic size, again, of the atom bound directly to the proton. And they're both oxygen, so there's no difference there. So the difference must lie in the inductive effect. So none of these. So first of all, let's say none of these are the factors in this case because they're the same as you go through it systematically. So now the only difference is there an electronegative atom that's near the proton? And there is. In both cases, there's a fluorine and a chlorine on the carbon that is adjacent to the one bearing the OH. So essentially what you need to do is compare the electronegativity of those two atoms. And we know that in terms of electronegativity, fluorine is greater, more electronegative than chlorine, which means that it's going to have a more of an inductive effect. So this essentially means fluorine has a greater, and I'll say IE for inductive effect, than the chlorine. So what this says then is that this molecule 2, or let's call it B, since we got a lot of stuff on here now that has 2. So this means that B is more acidic than A. Or in other words, B has a lower pKa than A. Okay, moving to the next question. Okay, so here let's go through this systematically again. So first let's look at electronegativity of the atom bound directly to the proton. So we're comparing then the oxygen to the nitrogen. And we know that oxygen is more electronegative than nitrogen. So in terms of electronegativity, oxygen is more electronegative than nitrogen. So in essence, that oxygen is creating a stronger dipole, so this proton has more of a partial positive charge than this partial positive charge on either of those protons. So right away that tells us then that, let's call this C and D to make it different from the previous question. So now D is more acidic than C. And then again, you can say it has a D would have a lower pKa than C. Now, we can go through all the other ones, just all the other factors, just to be complete. But we know in terms of resonance stabilization of the conjugate base, they would both just have a negative charge on the oxygen or nitrogen. There's nowhere for that to go. If it's a conjugate base, it can't delocalize anywhere. Third, hybridization is the same on all these. They're all sp3 hybridized orbitals. For atomic size, there is a slight difference between nitrogen and oxygen, but not significant to make that bond weaker in either case, really. So that is not the factor. So again, keep in mind atomic size matters most if you're looking at atoms in different rows on the periodic table. And then the inductive effect, there's no atoms that have electronegativity that aren't bound directly to the hydrogen. So that is not the reason here either. So it's just the electronegativity of oxygen versus nitrogen. Oxygen is more electronegative, hence the ethanol is more acidic than the ethanamine. All right, here we have our next question. So here, let's go through the factors quickly. So first, electronegativity, no difference because they're all just carbon and hydrogens. Secondly, conjugate base stabilization. There's no resonance here for either of them. 3 would be the atomic size. So I'll call that AS. There's no difference between atomic size there because they're all just carbon and hydrogens again. Fourthly, the inductive effect, IE I'll call it. Again, no difference, no chlorine or hydrogen or chlorine or fluorine rather, or anything electronegative nearby the carbons that we're interested in. So this must lie in the last factor, which is hybridization. Okay, so if we look at our first molecule, the alkane, they're all sp3. There is sp2 carbons in the alkene. So now let's call this A and this one B. So now we know from our factors that increasing S character will increase the acidity of the proton involved or near that increase in S character. So what that does is says that B is more acidic rather than A. Again, due to the fact that this one has 33% S character and A only has 25% S character. And once again, this means that B would have a lower pKa than A. Again, that could be the way the question was asked. Okay, let's move along here. Here's our next question. So again, if we go through our process, so first of all is electronegativity. There is a difference between the electronegativity of oxygen and sulfur. We know that in terms of electronegativity, oxygen is greater than sulfur, which would suggest that the OH bond is going to, that hydrogen is going to be more acidic bound to the oxygen. So let's keep that in mind. Secondly, there is atomic size difference. We know that in terms of atomic size, the sulfur is much larger than the oxygen, right? And then thirdly, no conjugate base stabilization, no inductive effect, and no hybridization. I'll just call hybridization HY. Okay, so now this question essentially becomes, is the electronegativity difference more significant or the atomic size difference more significant? And as I introduced with the atomic size factor portion of this video, if there is a difference in atomic size, that is more compelling, that's a stronger indicator of acid strength than electronegativity. Again, when you're talking about the atom bound directly to the proton, that's acidic. So what this tells us then is atomic size essentially wins. So D then is more acidic than C. Again, now D would have a lower pKa than C. And by the way, if you're curious about like how much more acidic it is, the pKa of a thiol is usually around 10, and the pKa of an alcohol is 15 to 16. So again, pKa is a log scale. So what that means is that this is on the log scale, this is 5 lower than, at least 5 lower than the alcohol, which means that this is 10 to the 5 more acidic than the alcohol, which is a lot more acidic. So this tells you how much more significant atomic size is than electronegativity for predicting acidic strength of protons. All right, here we have another question. So again, let's go through our checklist. So first of all, electronegativity, the oxygens are the same, bearing the hydrogen, so there's no difference there. Secondly, atomic size, the oxygens again are the same, no difference there. Thirdly, inductive effect. You could make an argument that there's inductive effect from this oxygen, increasing the acidity compared to just the hydrogens on that carbon there bearing the OH. That's true, but that's not going to be as significant as the other factor. But it's not wrong, so you could certainly say that. And then there is no difference in hybridization. Well, if you look at this carbon, this is sp2, whereas this is sp3. So again, you could make somewhat of an argument there, but that's not, again, that's not the huge factor. The biggest factor is the resonance stabilization of the conjugate base. So again, let's look at that real quick. So we have our conjugate base here would be this one, and our conjugate base for this, the alcohol, would be that. There's absolutely no resonance in the alcohol, but there is resonance in the acetic acid. This can go here, resonate up, give you this conjugate base, right? And then remember, our arrows are the double-headed arrow, not the equilibrium arrows for resonance structures. So again, now this says the greatest factor is that you have this resonance stabilization of the conjugate base. So A is more acidic than B. And again, you can say that A has a lower pKa than B. That's also fine. And if you're curious here, the acetic acid has a pKa about 5, and again, the alcohol is 15 to 16. So now we're talking about an order of 10 to the 10 difference, which is a dramatic difference in acidity. So all of these factors have a very large implication on the real reactions. Okay, moving to the next one. Okay, so here, there's no difference in electronegativity. That's the same. Secondly, no difference in atomic size, no difference in an inductive effect, and no difference in conjugate base stabilization. So this must lie in a hybridization, which it does. That is the key to this one. So these carbons are sp2 hybridized. These are sp in the alkyne. So what that means is there's more S character in our alkyne than in the alkene. So that means then that D is more acidic than C. Again, you could say D has a lower pKa than C. It's the same thing as saying it's more acidic. And if you're curious here what the difference is, the pKa of an alkyne is about 25. The pKa of an alkene is like 45. So basically the alkene is 10 to the 20 times more acidic than the alkene. The alkyne is 10 to the 20 more acidic than the alkene. So you would need a very strong base to pull off that proton from the alkyne, but it's possible and useful for many reactions. All right, here we have another question. So let's go through our checklist. So first of all, electronegativity. Is there a difference between the electronegativity of the atoms bearing the hydrogen? And there is. We know that bromine is more electronegative than iodine. Secondly, there is a difference in atomic size. This is very similar to the sulfur question. So atomic size, we have iodine is larger than bromine. And then there's no difference in any of the other effects. So there's no inductive effect, no conjugate base stabilization difference by resonance, and no hybridization difference. So again, now the question becomes, which one wins? Does the electronegativity win or the atomic size win? And as we've mentioned a couple times now, the atomic size is the more contributing factor to acid strength when it is comparing it to electronegativity. So what this means is B is more acidic than A. Or in other words, B has a lower pKa than A. Okay, let's move to the next question. So here we're showing the structure of H2SO4 and of HNO3. So first let's look at our checklist. So electronegativity. So electronegativity, we're comparing just this oxygen to this oxygen because that's the one bearing the acidic proton, or this one, that's also the same. There's no difference there. Then atomic size, there's no difference, again, of the oxygens that we are comparing. Thirdly, there's no difference really in hybridization because they both have sp. Well, this has an expanded octet, so there is some hybridization difference between the sulfur and the nitrogen, but again, that's not going to be the significant factor here. The two significant factors are the inductive effect and the conjugate base stabilization. So the inductive effect is essentially you have all these oxygens nearby that are affecting this proton more so than just the nitrogen. But again, that's a rather small argument. The biggest reason is going to be the conjugate base stabilization. So let's look at our conjugate bases and explain why one of them is going to be more acidic than the other. So here in the H2SO4, we have this conjugate base. Now, there's two resonance structures possible for this, where this negative charge can delocalize here and then up, or it can delocalize into the other oxygen. So I'll use a different color here. It could go here and then up. And I'm not going to show these resonance structures since we've looked at this several times, but you can have, if you follow the electron movement, you'll get 3 total structures. Now, if you look at the nitric acid conjugate base, you have this structure. And now again, there's only one resonance structure here. This one. There are more because you can put this, you can delocalize this negative charge as well, but that isn't what we're assessing for the acid strength here, right? You want to look at how the negative charge that's created from the acid-base reaction is delocalized. And here it can only be delocalized once. It cannot delocalize in any other way because this negative charge can also delocalize, but it won't influence this charge, which is the one that we're interested in. So then by all of this explanation, the H2SO4 is more acidic than the HNO3 because of the additional resonance stabilization of the conjugate base due to the fact that you have 2 sulfur oxygen double bonds. So now to summarize then, C is the sulfuric acid, which is more acidic than D. Or again, C has a lower pKa than D. These are both very strong acids. So don't get me wrong that the nitric acid, you can't remove that proton. You certainly can, and it's extremely easy to do so. But sulfuric acid is stronger, which may be relevant in, again, certain types of reactions that you need to perform. All right, here we have a different kind of question. It's rank the following molecules in order of decreasing acid strength. So in other words, rank the molecules in order of increasing pKa. So this is basically the same type of question, except we're given 6 molecules here. And we are asked to rank all of them in order of decreasing acid strength. So this can be a very taxing or seem very extremely difficult, but all you need to do is basically break it up into a bunch of the pair questions that we did in the previous set and then rank them all based on that. So in doing so, let's label these molecules. So we have A is sulfuric acid, B, C, D, E, and F. So I think the easiest to compare right away is B and C, because we have the same type of resonance of the conjugate base. We've looked at this a couple times now. If you have a negative charge there on that oxygen in the conjugate base, it can resonate up to the carbonyl. Same thing can happen here. No difference there. There's no difference in electronegativity, no difference in atomic size, and no difference in hybridization. The difference lies in the inductive effect of this fluorine. So the inductive effect is the explanation that C is a stronger acid than D. So here we can say C is more acidic than B. Okay, so that's one of our pairs. We know that. Now next, the next one that's easiest to compare, again, in my opinion, is E to F. We've done this question before in the earlier pairs. So E to F now. Again, the difference lies in atomic size this time now, because the sulfur is larger than the oxygen, so F is more acidic than E. Okay, so now we have a couple different ways that we can proceed here. So we either need to rank A to D, or we can compare these two sets. So let's just do A to D. Right away we see D has sp orbitals because of the hybridization, and A is extremely acidic due to all the resonance stabilization that it has. So if we compare A to D, we know that A is going to be a stronger acid than D. So let's write that down here. So A is more acidic than D. So this is A and D. So now we've looked at 3 pairs. But now the question is, we need to rank those pairs to each other. So if we go all the way back up, and we now need to compare which one is going to be the most acidic. Well, we know that A, B, and C all have resonance stabilization, which is the biggest, well, one of the biggest contributors to acidic strength. So we know A, B, and C are going to be more acidic than D, E, and F right away. So then the question is, among A, B, and C, which is more acidic? Well, we've looked in the previous question that sulfuric acid has 3 resonance structures total, whereas these two only have 2. So what that means is A is more acidic than C, which is more acidic than B. And we know that C is next because it has the inductive effect difference over B. Okay, and then I'll write this all down, but I want to walk through it here in just words first. And then now if we compare D, E, and F, we know that D has no electronegativity or atomic size difference. So, and those are more contributing factors than hybridization. So this is the weakest acid of these 3. And then we know that F is more acidic than E. So this order of decreasing strength is F is the strongest acid, then E, than D. So now let's write this entire list out, and then I'll give the reasons for each one. So we're going in order of increasing pKa. So our strongest acid first. This is let's say this is a pKa list. So A is less than C, which is less than still B, which is less than F, which is less than E, which is less than D. So now let's go through each one again and explain why, what is the reason for each difference. So if we go all the way back up, we know A is the strongest acid because it has this additional conjugate base stabilization. So the difference here is conjugate base stabilization of A to C because of the extra resonance structures that we talked about in the conjugate base. Now what's the difference between C and B? Well, that's the inductive effect. So this is the inductive effect because of the presence of the fluorine that is circled here. Then what is the difference between B and F? Well, B has this conjugate base stabilization that F does not at all. So that is the more contributing factor here. So the difference between B and F is conjugate base stabilization once again. Now what's the difference between F and E? Well, F and E, F has sulfur, which is atomic size difference. That is the reason there, because sulfur makes a weaker sulfur hydrogen bond compared to an oxygen hydrogen bond. So this is atomic size. And then lastly, E compared to D, it's simply that E has electronegativity bound directly to that hydrogen, where D only has hybridization, which is less of a contributing factor to acid strength. So this is simply that E has an electronegative atom, whereas D does not. So hopefully that makes it very clear of how you go about these process. It's very stepwise in ranking the acid strength. So that is all I have for this video. So I hope you enjoyed it. If you did, please leave a like and subscribe to the channel for more content like this. If you have a question or suggestion, please feel free to leave it in the comment section below, and I'll get to it as soon as I can. So I hope you all have a great day, and I'll see you in the next video.